Okay, we're going to continue on here. We're going to wrap up the kinetics chapter, and then we'll roll into the next one, which is equilibrium, I think. So last time we talked about a couple of things here with kinetics. We talked about the Arrhenius equation, which is our natural log of K2 over K1 equals E of A over R, 1 over T1 minus 1 over T2. Remember that this is really the sometimes referred to as the 2-point version of it, which what it really means is based off of the other Arrhenius equation, sort of the graphical one that we talked about, which is this one. If I could write, there we go, plus the natural log of A. This is our y is equal to mx plus b, which again gives us a natural log of k versus 1 over the temperature, which does need to be in Kelvin, given our straight line here, where it's equal to m is equal to minus E of A over R. So the 2.1 is really, technically speaking, you have a couple points off of this line, and you could really just kind of plug and chug into it. A couple important things that we talked about, it really doesn't matter when you're doing a problem necessarily which one you label as sort of K1 or K2, as long as the appropriate temperature that goes with those values do stay together. The temperature does need to be in Kelvin. And again, you do want to divide here first and then take the natural log of it. An important thing that I think we talked about, but just in case we didn't, we just re-emphasize sort of unit-wise here. We do want to be careful on the units of our E of A and R, which is a constant, which is 8.314 joules per Kelvin per mole, is in joules. And like I talked about before, typically speaking, a lot of times activation energy is in kilojoules. Now, it's not just a big issue if you're maybe solving for activation energy like we did in a couple of examples, but it is a big issue if you are not solving for activation energy and they give it to you, and maybe you're solving for a rate constant or a temperature or something like that. You do want to make sure always that these units do match. So you usually either got to convert 1 to joules or 1 to kilojoules. I personally will usually convert the activation energy into joules, so everything works out good at the end. But you do got to watch that. Otherwise, again, you'll be off by a factor of 1,000. So that's a very common mistake. Again, although we did solve for a lot of activation energy in our examples, as I mentioned, you could solve for any of these temperatures. You could also be asked to solve for any of the rate constants and stuff like that. So just making sure that you watch those units with the activation energy in R. We also talked about the idea that there are a few different versions of this equation. And again, some will have the negative, some will have sort of a combined fraction there in the parentheses. So I'm going to go with this equation like we talked about as the one that we'll use. We then got into sort of the idea of reaction mechanisms, and reaction mechanisms are really sort of plausible ways at which perhaps a reaction could take place. Not all reactions, as we talked about, happen in a sort of a one-step fashion. They could be individual sort of elementary steps that they occur. And when we look at elementary steps, they could be unimolecular, bimolecular, or termolecular, which means how many reactants are really reacting in each of these elementary steps. But there should always be perhaps a step in the mechanism, which is sometimes referred to as the RDS, or the rate determining step. And that is always really the slowest one in the reaction mechanism. And because it's the slowest step in the mechanism, it is the one that really determines the overall sort of rate of the reaction. So how we can determine sort of these things, and when we deal with mechanisms, are when we do have elementary steps, we can write rate laws using the coefficients as the orders. So remember, that is the only sort of place sort of in kinetics where you really can just take the coefficients and use them as the orders. Again, other than a reaction mechanism, you do need to make sure that you kind of find it experimentally, like we did with tables and stuff like that. Now, a lot of times, and not in all sort of mechanism problems, there are a few different variations of mechanism problems, but a lot of times you are asked sort of, is this perhaps a good mechanism? Is this a bad mechanism? And there's really kind of two things that you need to make sure of for it to be a good mechanism or a plausible mechanism. You need to make sure that all the steps add up to the overall reaction. So right off the bat, if you take all the steps of the mechanisms and add them together, remember canceling out anything that's an intermediate along the way, it should end up as the same overall reaction of what you were dealing with or looking at in the problem. The second one is the rate law for the rate determining step or the slow step should match the experimentally found rate law. So the experimentally found rate law a lot of times is given to you, not always in problems, but it is sometimes given to you. And that should have the same rate law as the slow step in the mechanism, because frankly, is the one that's determining how fast. Now, we saw a couple of problems where we have to sort of prove that or not prove that. And remember that we cannot necessarily directly always compare the rate law for the rate determining step to the observed rate law or the experimental rate law, because in some cases, and we did a couple examples last time, our rate determining step will have an intermediate in it. And when we write the rate law for the intermediate, as I mentioned, it's not really like kind of comparing apples to apples. So in those type of mechanism problems like we did last time, you do have to kind of use the other steps in the mechanisms, or maybe one of the steps in the mechanisms, to basically kind of substitute out the intermediate in your rate law so that you can get a rate law that really has sort of everybody that's involved in terms of reactants, so you can compare them. As we did in those couple examples, again, just looking at the rate law for the rate determining step versus the one that was found experimentally, without taking out the intermediate, you would look at it and go, they don't match. But as we saw, once we were able to substitute in for the intermediate, we saw that they actually did match. So again, it's really important to kind of get rid of that intermediate. And lastly, right, an intermediate does need to be made early on in the mechanism, but it does have to be completely used up by the time it's done. And an intermediate should not appear in the overall reaction. So we also had one where we did reduce something down as we were adding the equations together, but it still remained in the overall reaction. And again, that's why, I forget, I think it was like NO2 or something like that, maybe. And that's why it wasn't a intermediate, because it was still there. Yeah. They should never appear in the overall reaction. They will appear in the mechanism, and usually they'll be kind of made in an earlier step of the mechanism, but then they should really be sort of fully consumed by the time the reaction is done. So in a later step, they would technically be like the reactants and get kind of fully consumed as the mechanism continues. Other questions? All right, so questions on any of that stuff there? Yeah. Bless you. You probably won't really have one like that. There usually just be one that should be a slow step. There's usually one step in the mechanism that is really the one that's sort of like the guy in the 10 items or less line I was talking about the other day, it's kind of clogging up the line or clogging up the thing. And once you sort of pass that point, right, it kind of goes faster. You kind of think about like a volumetric pipette, right, where it has a little bubble in the middle, right? And as you're drawing up the solution, the slowest part of that is like the bubble part, right? Until it gets to the top of the bubble, and then it goes really quick up the pipette. So there's always sort of a step in that mechanism that will be really the kind of the slowest one and the one that determines, the overall rate of it. Other questions? Okay, so we have one more sort of mechanism type problem. It's a little bit different. So see what you come up with this. We want to determine what the overall reaction is based on this mechanism. We also want to determine which one's the rate determining step, and we want to identify the rate law and any intermediates there are. So take a couple minutes, see what you come up with here. All right, let's take a look. So obviously the overall reaction can be found by simply adding each of these steps together here. In this particular case, looks like maybe B. And I think that might be it. So at this point, if we add it together, we would end up with 2A plus B2 goes to 2AB in this case, I believe. Any questions on that so far? That also means that our intermediate here would be, yeah, it would be B here as it got completely canceled out. Just based on how this mechanism is labeled, we know the rate determining steps should be step 1 or step 2. Should be step 1 as it is the slow step. And because that is the slow step in the mechanism, we know that the rate law for that slow step should be the same rate law as should be found experimentally, which means, again, we can write a rate law here for our slow step, which would be K times A and times B2 in this case, which would be the rate law here for our first step. And in this case, this is again a different type of mechanism problem where we're actually using the mechanism to determine what the rate law should be. And then obviously in order to do that, they would have to be labeled slow, fast, and so forth. I think we hit all of this stuff there. Any questions on that there? Yeah. What's that? It'd be this one because it should match the slow steps rate law. I don't, because it is based not on the overall reaction, it is based on the first step, which is the slow step. And there's only one A in that case, yeah. It's not, it should always match the slow step. If it doesn't match the slow step, then it is not a good mechanism. It would not be a proper mechanism.
Rate law would be 2A, so the 2 does not matter.
It does not matter because in this mechanism, we're writing a rate law for each of the steps. So what I just wrote here is really for step number 1. And in step number 1, there's only one A. Just like you could write a rate law for this one, which would be the rate is equal to K times A times B for the second step. But this would not be what we would expect the rate law be for the experiment, because this is the one that's for the slow step. So it should match that one. Other questions? Yeah. The overall reaction is this right here when we add both of the steps together. Yeah. The rate law would be this guy. Yeah. Yeah. Yes. And even if it's given, it should also match the slow step if it's a good mechanism. So this type of problem would not be one where they would ask, is this a good or bad mechanism? So it's a different type of mechanism problem. This is one where they present you a mechanism, and based off of this mechanism, you could figure out, based off of this mechanism, what the overall reaction should be and what the experimentally found rate law should be for this one based on this. And this is different than the last 2 examples we did the other day, where they gave us the rate law that was found experimentally, and they gave us this mechanism. And in that type of rate law question, what they want you to do is basically prove either this mechanism that they gave you matches what they found experimentally, or it doesn't. So either it's a good or sort of bad mechanism. So there are sort of like 3 different types of mechanism type problems, like the one we did at the very beginning. Was a little bit different than this one. So there's kind of 3 different versions of mechanism problems you could come across. And it's based on sort of the information given to you and what they sort of want you to find. So in this case, we would assume that this mechanism perhaps is a good mechanism. And if this was a good mechanism for whatever reaction we're looking for, this would be all the stuff that should come out of that experiment. Yeah. Other questions? Questions on mechanisms here? All right, so to finish up this chapter on kinetics, we're gonna talk a little bit, just a little bit more here about a catalyst. We sort of been talking about it as we've been going through the different parts. But again, a reminder that a catalyst is typically a substance that's added to an experiment to speed up the rate of the reaction. Again, as we mentioned before, a catalyst, again, is not a reactant. It is not a product. And the important part is it really does not get used up in the reaction. So in most cases, the catalyst is just there to facilitate that reaction happening a lot quicker. And again, it could just be something as simple as a piece of metal that brings everybody to a centralized location so they can start reacting a lot quicker than if they had to kind of fly around. It could be something where perhaps like HCl, like we added in our experiment, that is a acid, creates a proper pH environment for this reaction to perhaps occur a lot quicker than it would if the pH was, say, a different sort of level. So catalysts find an alternative pathway for something to happen, kind of like the old cartoons, right? The coyote has to go up and over the other side, right? The roadrunner opens a trap door in the mountain and goes just straight through to the other side, right? And he gets there a lot quicker. So, by finding that alternative pathway, it allows for the reaction to occur. Ultimately, what it's doing is it's actually finding that alternative pathway. It's going to lower that activation energy. So that is typically how a catalyst works, is it tends to lower the activation energy. The result of lowering the activation energy by finding that alternative pathway is it will typically increase the proportion of molecules that have enough energy now to get to the other side. So because now the hill is much smaller, you could get to the other side. There's more people that can make it up the hill, right? So, again, it's like if we were running up a giant hill, right? Straight uphill. And there's going to be a few people that could run all the way to the top and get down to the other side of the hill, right? But if you had to run over like a speed bump in the parking lot, that's not a very big hill. Pretty much a lot of people could get up and over to the other side. And that's basically the idea here. So lowering that activation energy allows the rate constant to increase and thus the rate of the reaction to increase as well. So we do see an increase in the rate. Now, there are some different types of catalysts, and a lot of times we do talk about catalysts as speeding up a reaction. There are actually some catalysts that sometimes people will add to slow down a reaction. They are sometimes referred to as a negative catalyst, but I would say probably 99% of the time if somebody is talking about a catalyst, they're probably thinking about it in terms of speeding up that reaction. But you should be aware, again, there are some that can kind of slow down a reaction as well. Now catalysts can be heterogeneous catalysts, and heterogeneous, just like heterogeneous mixture, means you see different layers. So when a heterogeneous catalyst, that means that the reactants and the catalysts are in different phases. So maybe they're gases and the catalyst is a solid, and that would be a heterogeneous catalyst. So something like the synthesis of ammonia, N2 plus H2, making some ammonia here. Again, a very slow reaction will take place, but it will take a long time. But the addition of a catalyst allows really these gas molecules that are flying around, again, to sort of hit a centralized location. Production of nitric acid, catalytic converters, right? In our cars, there's 2 chambers. They're filled with certain metals and stuff like that that help cut down on emissions as well, but by doing a reaction. Homogeneous catalysts are when the reactions and catalysts are in the same sort of phase, usually liquids. And for example, the experiment we've been doing, we have that sort of HCl, right? It's basically the same phase. It was a solution like everybody else. And again, in this case, it may just be creating a different environment to allow the reaction to occur a lot faster. And here's the idea of the Haber process here. Again, you can see some iron or aluminum, some potassium oxide. And again, this is the catalyst here, and you can see without it, the gas molecules are just sort of flying around. But with it, it actually kind of attracts everybody to it. It also helps with these guys kind of breaking apart as they're kind of sitting on there, and thus would help a lot quicker sort of rearrangement into ammonia on the other side. So again, that's sort of the idea of a solid catalyst. Nitric acid here as well, platinum wires used to make nitric acid. It's actually a multiple step sort of process. And part of the nice thing of this process is it actually makes this guy, which can then break down and actually produce some of the other parts of the thing. So it's kind of a double whammy in making the nitric acid. Here's our catalytic converters, which is used to help us with unburned hydrocarbons so we don't pollute too much, but there's usually 2 chambers. A lot of times it's like a honeycomb type design in our catalytic converters where there's a lot of precious metals, which is why people steal your catalytic converters off your car, right? And stuff like that. They used to do a lot of it out here in the parking lot. People go out and go, oh, they sent out an announcement once. If you see somebody with a circular saw walking around, you should report that because they're probably trying to steal your catalytic converter. Just envisioning that picture of somebody walking around. But yeah, so we have basically 2 parts, just 2 things. And obviously that's what they test, right? Part of what they test is the emissions coming out of your car, right? If you get a smog check. And if it's too high, that means perhaps these aren't working so well anymore. And the reaction that kind of gets rid of those pollutants is not as effective, right? Because the catalyst isn't working really well. So you need a new catalytic converter. All right. Any questions on catalyst there? Yeah. Homogeneous catalyst basically means that the catalyst and the reactants, they're in the same phase. So very much like the experiment we just did, the HCl, which is really a catalyst in that reaction, is a solution, just like your other reactants were solutions. So they're all in the same phase. And that's different than, say, like the metal here, a piece of metal like this is a metal versus the reactants, which are gases. They're flying around. So that would be more of a heterogeneous type of catalyst. Other questions? Yeah. No, you just need to know generally what a catalyst is and how it, how it works to speed up a reaction. Okay. Other questions? All right, so we're gonna wrap up that chapter here. We're gonna roll off to the next one. Okay, so the next chapter we're gonna talk about is really the start of the class. No, I'm just kidding. It's the start of really the big calculation that we're going to do for a good majority of the class. We're going to learn it here in this chapter, and we're going to learn about every equilibrium sort of constant that you never want to know about. So really this part of the class is brought to you by the letter K, which is the equilibrium constant. And like I said, we're going to learn every single K that you probably don't want to know. So let's talk first off about equilibrium. And when we talk about equilibrium, it really is talking about a specific type of reaction, and it's talking about a reversible reaction. And a reversible reaction you should be familiar with. These are the reactions where we see arrows heading in both directions. So in a reversible reaction, as we talked a little bit about maybe when we were talking about mechanism a second ago, it basically has 2 directions. It has, again, a forward direction. And in the forward direction, that would be the reactants going to the products. And at some point, what's going to happen is you're going to build up enough products that they will decide to start reacting with themselves and head back the other way. And that is what is referred to as the reverse direction. And at some point, what's going to happen is this reaction will reach what is referred to as chemical equilibrium. And there is a very big misconception a lot of students have about what the word equilibrium means. They hear equal and they think equal. And that is not what chemical equilibrium means. It doesn't mean that when you reach chemical equilibrium, you have the same amount of everybody on each side. That's really not what it means. It actually means more of what we were just talking about in the previous chapter. It means more about the kinetics of what's going on. It means that when it reaches chemical equilibrium, the rate of the forward reaction will equal the rate of the reverse reaction. So that is essentially what it means when it reaches chemical equilibrium, that just as fast as it breaks down into products, those products will just as fast recombine and head back the other way and really make back your reactant. So what does that do when something reaches chemical equilibrium? Well, frankly, it locks everybody into place in terms of where they're at that point. So for example, if we were at A plus B D plus D, and we'll just say we started with 4 of A and 2 molar of B, and we had none of these. And then we basically reach equilibrium down here, right? And then we maybe have, say, 3 of these, 1 of these, maybe we got 4 of those, 2 of those. What that means in terms of once it reaches equilibrium, if those were, say, the concentrations of everybody, those concentrations will pretty much remain the same, because just as fast as we lose a little bit of reactants, they come back. So it's really a nice balancing act that happens when you reach equilibrium. So the first really main misconception that people have is everybody should be equal on both sides. What is equal is the sense that it locks everybody into place and they will not change unless you do something to screw up the equilibrium. So as long as you don't do anything to kind of mess up the equilibrium, which we'll talk about messing up the equilibrium a little bit later on in this chapter, but as long as you don't do anything like that, once it reaches equilibrium, pretty much everybody's locked into where they're at in terms of either concentration or even in terms of pressures if you're dealing with gases. So their pressures would be locked into place as well. So when we look at chemical equilibrium, it is the state, as I mentioned, where all the reactants and products remain constant with time. And when people look at a reaction that perhaps has reached equilibrium, you may look at something and maybe it turned red, or maybe it was red and then it turned colorless, or whatever it may be. When you look at, say, the beaker, the flask, the test tube that it's in, it may look like really there's nothing going on. You know, it may look like the reaction's over, not much is changing. And that's because everybody has pretty much gotten locked into places to where they're at. But if you're able to like super zoom in and see what's going on, there is a lot of activity. There's a lot of reactants going to products, but just as quickly, there are products coming back to reactants. So on the sort of microscopic level, there's a lot of activity happening. But sort of on the macroscopic level, when you look at the big picture, it just looks like not much is going on. But so there is still a lot of activity that happens even when a reaction reaches chemical equilibrium. And that's why sometimes it's said on the macroscopic level, it is static. Not much looks like it's happening, but definitely very dynamic on the microscopic level, because in order to maintain everybody exactly where they're at, those rays got to kind of constantly be going back and forth with each other. The forward reaction has to be happening. The reverse reaction has to be happening as well. And that's what we see here. This actually is the production of ammonia that we were just looking at, N2 plus H2, making our NH3. And we can see initially here at the start of the reaction, it is all reactants. So we pretty much have all reactants. We have no products happening here. So because at the very beginning here at time 0, it's all reactants, no products, the only thing that could really occur at the very start of this reaction is the reaction has to head in which direction? The reaction has to head towards the product side, right? Because all we have are reactants, which means they're going to start reacting, right? And that's going to start to decrease the amount of reactants, which is what we see in this graph. It should also at that point start to increase the amount of products that we're making, right? Now, at some point, what's going to happen is we're going to get enough products that they're going to decide we're ready to come back the other way, right? So there's sort of a buildup until you get a good amount of products that they will then start reacting and coming back toward the reactant side. And we see that starts to happen right around here because the slope of this line gets a lot less, right? So we're not making as much product at this point. We're actually decreasing the amount of product. We're kind of leveling off. And we also see that we're not losing as much reactants as well when we kind of hit that point, right? Because the products are now making some of the reactants. At some point, what will happen is right around this spot right here, we pretty much have hit chemical equilibrium. And we know that from this graph because at that point, everybody is now locked into pretty much the same concentration. Their concentrations are no longer changing, which means at that point, we've hit the rate of the forward reaction and the reverse reaction basically equaling each other, which then locked everybody into place. And once again, they will continue on this path as long as you don't do anything to kind of screw up the equilibrium. Any questions on that there? So let's take a look at this reaction here and talk a little bit about what's going on. So initially, we have no H2 or CO2 present. So the only option for this reaction would be the forward reaction, right? So the forward reaction would happen because there's a plentiful of reactants. So we talked about what's necessary for a reaction to sort of increase its rate or the rate of reaction. The presence of all those reactants means they have no option but to start reacting and making products. As we start to build up our products, we will then start to get some of these guys to work their way back. And once again, as we've been talking about, it will continue until we hit a equal rate of that forward and reverse reaction. And that's what we see here. So graphically on a graph, pretty much wherever it sort of plateaus out that line, that means we're really not making any more reactants or products. Everybody's maintaining where they're at. And that's really at the start of that is where, you know, equilibrium has been reached. Again, in this case, before that step, we were losing our reactants, we were making our products, and then we're kind of slowly making a little less products, losing a little less reactants until the point where, you know, it kind of levels out. So let's take a look at the same reaction here and let's think about what will happen to this reaction if we're at equilibrium. So we let this reaction reach equilibrium, and then we decided that we would like to add some more H2O to this flask. So how will all the concentrations change? So take a moment to kind of think about how all the concentrations of both the reactants here and the products would change. Would they increase? Would they decrease? Will they stay the same? Take a moment and kind of think about it, and we'll talk about it, what we think will happen here. Okay, so we have the system is at equilibrium. I decide I'm going to throw in some more water, some steam in here. Let's start with what is going to happen with the CO concentration. Will it go up? Will it go down? Will it stay the same? That's a 33 1/3 opportunity there to have the right answer. I would do the other math like the 66 and a 0.6 chance of the wrong answer, but that's all right. Yes. So you're on the right track here. So let's just think about it logically here, right? When I add water to this reaction, am I adding more reactants or products? I am definitely adding more reactants, right? That means there's going to be a greater amount of reactants available there, right? To start reacting, right? A lot more water. And that should actually kick off which reaction did happen, the forward reaction or the reverse reaction. Yeah, so because the presence of the extra reactants, the CO is not going to have trouble finding a water to start reacting with, right? Because there's a lot more there. So that really should kick off the forward reaction happening in this case. That means that, as you correctly said, we would expect our CO concentration at this point to start to go down, right? Because in order to make products in that forward reaction, we actually need both reactants, right, to come together to make our products. That would mean then on our H2 side here and our CO2 product side, those concentrations should then do what? They should go up because the forward reaction is happening and we're making products. So we should expect these guys to head up, yeah? Now, what will happen with the water here? Well, it's first going to go up because frankly, you added it. So you artificially added more of it. But once you're done adding it, it then should start to do what? It should start to work its way back down, right? Because as it starts reacting with the CO, you're going to need some of that water. So in the case of the water, it might be hard to determine exactly where you end up. You might actually end up higher than you started with because you threw some in there. So, you know, it's not possible. But what you definitely should see is you'll see a spike in it because you added it. But once the forward reaction starts, you should start seeing that water come down with the CO as they are reacting to make our products. Any questions on that there? All right, so same reaction, but in this case, we add some H2. How is everybody going to change in this case? So let's start with the H2O. What should happen to the H2O in this case? It should increase. So let's talk about why that is. In this case, we're adding H2, which is actually a product, right? So that's going to make a lot more products available to each other, which means the forward or the reverse reaction should actually take place here. Yeah, the reverse reaction should really kick off in this case. And that is going to cause our H2O to increase because we're making more reactants in this case. It would also cause our CO to head upwards as well for the same reason. Our CO2 should go. That's a 50-50 shot on that one, by the way. It should go down, yes. We'll just keep percentaging out everything. So it should go down for the same reason. That reverse reaction is going to kick off, which means we should see a decrease in our CO2 because the CO2 and H2 have to react to make our reactants in this case. And in case of the H2 here, we'll see a very similar thing that we just talked about with the H2O. Again, it will artificially kind of jump up there because you added it. But once that reverse reaction really kicks off as a result of that, we should see it kind of work its way kind of back down as it's reacting with the CO2. Any questions on that? All right, and that's the same graph. I liked it so much, I put it in twice. All right, let's talk a little bit about the equilibrium constant and its applications. So this is the big letter of the season here, which is the equilibrium constant. So capital K is the equilibrium constant. And since we talked about kinetics here, lowercase k is the rate constant. Yeah, so make sure you either capitalize or don't capitalize, especially on reports. Usually around this time, everybody's doing capital K's for rate constants because they got it in their head. So rate constant, lowercase k, capital K, equilibrium constant. For this particular reaction here, we take our reaction, and really to calculate equilibrium constant, it's basically the concentration of our products divided by the concentration of our reactants. So that is essentially how you calculate the equilibrium constant for any reaction. You take your products over your reactants. Now, there's an important thing that we also do, which is the coefficients in the balanced equation do become our exponents. So that is why we take the C to the C, the D to the D, the A to the A, and the B to the B. So you do have to take the coefficients into account here when you write the equilibrium constant. And this is what is sometimes referred to as the Kc value. C, I'm assuming, means concentration. And that is what those brackets mean. I think we've talked about it before, but once again, the brackets do mean concentration. And usually that is molarity that we are talking about here, moles per liter. Yeah. So if you take the products divided by the reactants, you will get the equilibrium constant. And since it is called the equilibrium constant, that means that value should be a constant value for a reaction. No matter what happens, it will always be the same number. The only thing that will actually affect the value of the equilibrium constant is temperature. So changing the temperature will change the value of the equilibrium constant. So temperature is the only thing that changes the value of the equilibrium constant. So there's an important part about that. What that means is if you are comparing the equilibrium constant, say at 25 degrees Celsius to the equilibrium constant at 50 degrees Celsius, they will be different numbers. If you then do your reaction at 50 degrees Celsius and you started with all reactants, you started with some reactants, some products, you started with a little bit of products, no reactants, it will always be the same value. It will always come to rest as the same ratio of products to reactants. They will all be basically the same K value. If you move down to 25 degrees Celsius, it will be a different K value than 50 degrees Celsius. But if you stayed at 25 degrees Celsius and did a bunch of experiments with different amounts, it will always be the same number in terms of the equilibrium constant. So temperature is the only thing that changes the value of it. We could have different amounts, and this is also something very hard for people to wrap their head around, which is, hey, in this reaction, I did 5 molar of the first reactant and 6 molar of the second reactant. But in this next one, I did 2 molar of the first reactant and 3 molar of the next reactant. How can I get the same equilibrium constant value? I did use different amounts. So the amounts doesn't really matter. It will always come to rest of the rate of the forward reaction and reverse reaction with the same proportion of products to reactants. So to illustrate that with numbers, we like numbers, yes. If I take, for example, 8 divided by 2, what does that equal? 4. Hoping so. All right, I take 16 divided by 4. 4. 4 divided by 1. They all ended up at, they're all different numbers, yeah? So regardless of, the amount that you start with reactions or products in any reaction that's an equilibrium reaction, the ratio of what you end up with in terms of products to reactants will always end up as the same ratio, regardless of how much you start. So again, it's a very common mistake a lot of people make, that they think, well, I started with way more here than I did in this reaction of reactions or products, so I should get a different value for the equilibrium constant. And that's not the case. So as long as you don't change the temperature and you do a bunch of different reactions, temperature is constant, you'll end up with the same ratio. Yeah. That's actually what I was just going to talk about, which is a good question. The actual answer is there are no units. Yeah, they won't always cancel out perfectly, but because of that, they won't cancel out perfectly. We typically do not use units for the equilibrium constant. So the equilibrium constant is just a number. So frankly, it's just a number, no units. I've only seen one person in my all years that would put units, but nobody really does put units, and you really shouldn't use units at all, because really they don't cancel out perfectly in a lot of cases. So it is really just a number, no units, which is great. The other thing is it does tell us some things, though. This number is an important number because let's say I had a large value of K. What does that mean? When I reach equilibrium, would I mainly expect to have reactants or products at a large value of K? It would be products, right? So just mathematically speaking, if you have a large number on top and a small number on the bottom, you will get a large number, right? So a large value of K will tell you that when you reach equilibrium, you would mainly expect products to be present. And opposite of that, obviously, would be if you had a smaller value of K, you would expect more reactants to be present. Again, the opposite logic here, smaller number up on top, larger number on the bottom, will give us a smaller number. So the value that you see for Ks is really important because it does give you an idea as to what you would expect to perhaps be there when you reach equilibrium, mainly reactants or products. There are definitely different degrees of that, and we'll talk about them as we go through all the different K values. There are some K values that are times 10 to the 30, 40, 100, and there are some that are times 10 to the minus 32, super small numbers, really large numbers, and anywhere in between. But in general, if you have a large value of K, you should mainly expect to be products there. A smaller value would mean you expect mainly reactants. So what is a large value of K? Well, the large value is that big number 1 there. So 1 is considered a large value. So anything above 1 is considered large. Anything less than 1 in terms of the equilibrium constant is considered a small value. So for the most part, anything with a negative exponent will be considered sort of small. Anything with a positive exponent or just like a whole number with no scientific notation would be expected to be a large value. Any questions on that there? So here we have this reaction. We got Mickey Mouse before he went to Disneyland, and then he was happy afterwards and jumped upside down. But we have a K value here of 25. And that would mean that at equilibrium here, we would expect mainly reactants or products. Yeah, that 25 is larger than 1, so it would be expected to have mainly products. That does not mean, does that mean that you would have, say, no reactants? No, you would have reactants. Even in a really extreme case of a very large value of K, or even a really small value of K, it is still ultimately a reversible reaction. So there is still always going to be pretty much something on both sides. It could be super small on one side that it's almost like all gone to the product side. It's almost all like a one-way street, but it will still come back a little bit of it will break apart, like super small amount. But there will always be a little bit of something coming back the other way. So when we talk about equilibrium, there is what is referred to as a homogeneous equilibrium. And a homogeneous equilibrium, that means everybody's in the same phase. So if we wrote our equilibrium constant value here, which is our Kc, concentration of our products, again, the 2 here ending up here, divided by this, which obviously is a 1, which is why we don't see anything written there. It's assumed to be 1 in this case. Now, these are gases, which means sometimes we may not be looking at concentrations with gases, but we may be looking at pressures. And we remember our PV equals nRT, yes. Ideal gas law. Yeah. Pressure needs to be in atmospheres, right? V is volume in liters, N is moles, T is our temperature in Kelvin, and R is 0.08206 liters atmosphere Kelvin mole, or 0.0821 if you use that rounded number. So we can actually write an equilibrium expression that deals with pressures, and it's done the same way, and that's what we see here. The Kp value, and P standing for pressure, I'm assuming in this case, is the partial pressure squared of our products divided by the partial pressure of N2O4. So we could actually write a Kp value, which deals with partial pressures. Clearly, to write a Kp value, you need gases. So if your reaction doesn't have gases, you cannot write a Kp value, right? Because there's no gases, no pressure. You don't have to worry about it. But if you do have gases like we have here, we do include it. I'll jump the boat here in the gun, and we'll talk about it a little bit later on as well. But really, when we write an equilibrium constant expression, there's basically 2 things that we do not include, and there's 2 things that we do include. So when you are writing K expressions, anything that is aqueous, which is a water environment, basically a solution, and anything that is a gas are included. Anything, as we will see here, that is a solid or a liquid are not included. And that is because, as we will talk about, if it's a solid, it is pretty much sitting there, not doing much, right? And if it's a pure liquid like water, its concentration is relatively constant because it has a pretty high concentration. So it doesn't really change all that much during the reaction. So those 2 things are not usually put into ever in a equilibrium constant expression. So really the 2 things that you should always put in there is anything that has an aqueous symbol next to it or a gas symbol next to it. Now the Kc value and the Kp value in most cases are not usually numerically equal to each other. Like they don't have the same numerical value. It is possible they can, but in a lot of cases, they're not the same numerical value. But what they do tell you is the same thing. So if you have a large value of Kc and a large value of Kp, they both mean the same thing, that you would expect to mainly have products at equilibrium. And if you have a small value of Kc and a small value of Kp, they both mean the same thing. You would expect to mainly have reactants. So they do tell you kind of the same thing. Numerically speaking, they oftentimes are not the same number. But there is a way that we could go between Kp and Kc, which is sometimes helpful depending on the information that's given to you. So the Kp value is equal to the Kc value times R times T. R again is our gas constant here. It's actually this version of it, not the energy one that we were using. So it is the 0.08206 or 201, whichever one you like there. T is our temperature in Kelvin. And obviously Kp is our equilibrium constant for pressure, and our Kc is our equilibrium constant for concentration. Delta N is the change in the number of moles of gas that are present, and that is our products minus our reactants. So for example, if I had do 2A plus B goes to 2C. What would delta N be in this case? It would be -1. So delta N here would be our products, which by the way, you just count out the coefficients. So that's anything with a G. So that is a 2 minus, that's a gas. So there's 2 of them there. That's a gas. There's 1 of them there, which is -1. It's really important to do products minus reactants because another very common mistake that people make is the difference is 1. And although you may not think that's important, mathematically speaking, when you go into RT to the first power versus RT to the -1, is it mathematically different? It is. The -1 is 1 over it, right? So it is really important to make sure you do the products minus the reactants so that it will not screw up the math part of the calculation. Yeah. Yeah, so clearly to either to get the value of the Kc or the value of the Kp, for the Kp, you would need partial pressures given to you. And by the way, they would need to be equilibrium partial pressures, right, to put it into that expression. And for the Kc, you would need, again, equilibrium concentrations to go into that. And now you could have a problem where, for example, they wanted you to figure out what the Kc value is, but maybe they just give you the pressures. So the only thing that maybe you could calculate at that point directly is the Kp, and then you can use this formula to swap it out to a Kc value without knowing the concentration. What's that? It is. It's based on your given as to which one that you would use, and obviously what would make sense. So if you're given pressures, you could directly calculate a Kp. If you're given concentrations, and again, their equilibrium of both of those, you could calculate Kc. Other questions? Yep. Other questions? So our homogeneous equilibrium, like for example here, which is our acetic acid, which is this guy, acetic acid, dissociating to acetate and a little hydronium ion. If we were to write our equilibrium expression here, we would do our products over our reactants. As I just mentioned, kind of jumping the gun a little bit, water is going to have a pretty constant concentration throughout the whole thing. It's not going to really change all that much. So we typically do not include it here. And that means that the correct Kc expression for this reaction above would be the one I just boxed there. It should not include water. So again, we do our products over our reactants without water being there. And as we talked about earlier, we generally don't use units for it. It is just a number. So once again, anything that's a liquid, anything that's a solid really are not going to participate in the equilibrium, and you should not include it in the expression. Only aqueous things and things that are gases. All right, so why don't you take a moment here, write the Kc and Kp for this, if possible. And here we'll write our Kc. And once again, it's going to be our product. So that's going to be the concentration of NO2. Once again, here we do need to take it to the 4th power because of the coefficient. We're going to times it by the O2, and again here that's 1 basically, so you don't have to write it. It's assumed to be 1 there. We're going to divide it by our reactants, which would be the concentration of N2O5, and once again here taking our coefficient, and that is it on that. And for the first one here, we can write a Kp value. We got gases going on there. It would be pretty much identical, except that that would be the partial pressure to the 4th of NO2 times the partial pressure of O2 divided by the partial pressure squared of N2O5 in this case. Any questions on either of those? Coming to the bottom one here, we will do our Kc, which would be the concentration of H3O plus times concentration F minus divided by the concentration of HF. And do I include the water? I do not, again, because it's a liquid, so we would not include it. Can I write a Kp for the bottom one? Can I write a Kp for the bottom one? I cannot, because there's no gases, so you cannot write a Kp for the bottom one. So you do need some gases in there to be able to write it. Question on that there. Now, what happens if I had something like something? I don't know. We'll do 2A goes to B. Say something like this. It's a solid, maybe, or something like that. How would I write the equilibrium constant for this? K would equal 1 over A squared. So you just use a 1. If there's something on the right-hand side you can't include, you would obviously just use a 1. Just like if you had something like this. These sort of say aqueous. In this case, the Kc would really just be our products in this case. Again, we wouldn't include this guy as it's a solid. Yeah. No, so typically you would need typically you probably have in most cases either like a solid with that, like something went through a decomposition that maybe produced it and stuff like that. But you need at least a gas to include it for the Kp value and stuff like that. So you probably won't run into too many cases where you'll have like a combination of all those things that would be included and not be included kind of thing. So if it's something where maybe you had a solid that had decomposed into like a gas or something like that, that would probably be more what you would see. Yeah, those are the only ones that should be included in the equilibrium expression. Solids and also liquids should not be included. And that's why we didn't include the water here. And that's really for the 2 reasons that we sort of talked about. They really don't participate solids. They're just kind of sitting there like a rock, if you will. In order for a solid to really participate, it would have to dissolve, right? And when it dissolves, it's no longer a solid. It would be ions in that case. So that's why it really doesn't participate. Why don't we try one here, wrap it up with the equilibrium concentrations of this reaction for carbon monoxide, I'll spit that out, monoxide, and chlorine to form COCl2 is 0.012, 0.054, and 0.14. We're looking for both the Kc value and the Kp value. So see what you come up with here. To look at since we're getting to the end here. So logically speaking here, which one would make most sense to solve for first? Yeah, the Kc, because we do have the concentrations given to us. So that's just like a plug and chug type of deal. So we're going to write our Kc expression here, which is going to be our products, which is our COCl2 divided by our CO and our Cl2. And in this case, we're just going to pop everybody in the right spot. So it's going to be 0.14. Our CO is 0.012 and our Cl2 0.054. And if you do all that good stuff, that's like a 216, or if you're concerned about sig figs, like a 220, like it's a chemistry class, one of those things. I don't know. Any questions on that calculation there? Yeah. Uh, 220 is fine, like that's where you can write it, you can write it either way. I don't prefer one over the other. You should try to get obviously the right sig figs and all that. And since it was asking for this as an answer, you know, maybe 220 might be the right one to go with. At this point, now that we have the KC value, we could use that equation, that formula that we saw earlier, which is the KP times the KC, RT delta N. So we do need to do a couple things here. First off, our temperature is not in Kelvin, right? So we got to convert that to Kelvin. So our temperature in Kelvin, again, that's a 273 on that conversion. And that's going to give us a 347, I think. We also want to figure out our delta N in this case. And our delta N in this case is the number of moles of gases. So on the right-hand side here, product side, we have one gas molecule. Minus on the left-hand side or reactant side, one gas molecule there and one more there makes 2. So that's going to be a -1 in terms of our delta N. Any questions on that there? R is the gas constant. So again, I use this number because it was beat in my head, but if you want to use the 0.0821 number, that's all right as well. And that should be everything we actually need now on the right-hand side, if I'm not mistaken. So KP would be, and again, depending on which one you want to use, I'll use the 220 here in this case. We're going to do our 0.08206 and our 347. And then take that whole thing to -1. By the way, you want to multiply first here and then take it to the -1, right? So we're going to do a 0.08206 times 347. Which gives you like 28.47. And we're going to do 1 divided by that number, which is basically the 1 over it. Gives us 0.0. We get this guy out like 0.0351187. And now we're going to multiply it by the 220. Going to get us about a 7.7 as our KP value. If you use 216, you got 7.6, I think. Yeah. Question on that calculation. So this is where that formula can be helpful. Obviously, we're given just pressures. I'm sorry, just concentration. Particular situation. By the way, this would mean that we would mainly have reactants or products at equilibrium here. Products, yes. And we kind of see that a little bit there. We got a larger concentration of products, right? So that's good. Any questions on any of that?